Hey, this is Jainil, and I will be your TA for this course. This is my second time teaching the course, and the material is slightly different than the last time, and it is more inclined towards computer science, and I feel it should be fun. This course should provide you with tools to approach different problems in computer science, and specifically proving problems. Um, We will start with basic definitions in discrete math, and today we'll go over the pigeonhole principle. I'll be taking the discussion sections majorly and doing a few homework gradings. My discussion sections would be in this order. We'll start with theory, revise some theory from the lectures, practice a few questions, and you'll have real time, some time to solve the questions before you see my solutions. And I'll go over, I'll review what we undertook during the discussion sections, and then I'll be open for queries, and then we'll wind up the discussion section. So I think it should be very open-ended, and feel free to ask me any questions or suggestions if you have it. A set is a collection of things or elements. As you can see, the set A that I've written here is yellow, blue, and orange. That is a set of colors. The elements that belong to a set are called its members, and all members must be distinct, but the order does not matter. So if here the set A was blue, yellow, orange, it would still be the same set A. Next, let's define integers. Integers are all positive, negative, natural numbers with 0 included. Real numbers are all the numbers that you can define or show on the real number line. Negative numbers are less than 0, positive numbers are greater than 0, non-negative numbers are greater than equal to 0, and non-positive numbers are all numbers less than equal to 0. So that is like all numbers that are non-positive and all non-negative. A set can be finite or infinite. Finite sets are those sets that can be listed in full, like you can write those elements down. The number of elements in a set is called the size of the set or the cardinality of the set, and it can be defined in these two ways. Infinite sets are the ones which are not finite, that they cannot be listed down. Let's do a question. You're given a set A that has 3 elements, 1, 2, 3, 4, 5, 6, 7, 8. You might just have found the answer from me. The question is, given this set A, list the elements and find the cardinality or the size of the set A. And let's take 1 minute to try to, half a minute to answer this question. Alright, let's look at the answers. I said there are 3 elements. So the elements are 1, 2, 3, 4, 5, and the set 6, 7, 8. So 3 elements, and the cardinality, that is n of A, is 3 because there are 3 elements in it. Let's look at the next question. List the elements of each set given the natural number set 1, 2, 3, like all numbers, all natural numbers. You have to write 3 sets down. The first one is A, that x belongs to natural numbers and x is greater than 3 and less than 9. X is a natural number, x is even, and it is less than 11. And x is a natural number, and 4 plus x is equal to 3. Let's take 20 more. Let's take 40 seconds to answer this question. So I'll just repeat the question again. You're given the set of natural numbers n is equal to 1, 2, 3, 4, all the numbers you can think of. And you need to write 3 different sets. The set A is x belongs to n, but x is greater than 3 and less than 9. Second set B, that is x is even and x is less than 11. and the third set is 4 plus x is equal to 3. Okay, let's look at the solution. So the first is x is less than 3, greater than 3 and less than 9, so you have the elements 4, 5, 6, 7 and 8. The second one is x is even, so all the even numbers that are less than 11 and are natural numbers, that is 2, 4, 6, 8, 10. Now if you look at this equation, 4 plus x is equal to 3, no solution would be present in this set 1 to 3. It will be negative, so you would have no element in this set, and hence the set would be an empty set. Let's look at what a function is. A function is a rule that associates members of one set to another, such that each member of the first set associates with exactly one member from the other set. And usually it's written as f belongs to x to y, and where the small x is the argument that belongs to the first set, and the f of x belongs to y, that is the mapping of x to y, and fx is the value of the function on that argument. That's what a function is. I have 3 balls, 2 boxes. Can I say there is at least one box that will always have 2 balls in it? So I'm just saying that if I put the 3 balls into the boxes, and whatever or whichever way I put it, there will at least be one box which has 2 balls or more in them. Can I say there should be at least one way that at least one box will have 2 balls? So I'm placing the 3 balls into the boxes, and I want to see if there is any way I can see that always there will be one box that has 2 balls in it. So let's start by putting one ball in it. The first ball is placed in the first box. It could be either of the boxes. I put the second ball in the same box. So now I do have at least one box which has 2 balls in it. And I can put in the third ball wherever, but I still have one box which has 2 balls in it. The other approach would be the first ball is placed in the first box. The second ball is placed in another box. So I have 2 boxes with 1 ball each in them. Now I place the third ball in either one of them, I will have at least one box which has 2 balls in it. So did you see something? If I had 3 balls in it, no matter whichever way I placed it, there will always be one box which has at least one box with 2 balls in it. So that was the intuition for the pigeonhole principle. If I had n pigeonholes which were occupied by n plus 1 or more pigeons, then at least one pigeonhole is occupied by more than one pigeon. I'll repeat that. If n pigeonholes, so the pigeonholes in our cases were the boxes, so we had 2 boxes in them, and n plus 1 or more pigeons. So if n was 2 and I had 3 or more pigeons, then at least one pigeonhole will be occupied by more than one pigeon. So that was sufficed for our question. This is the formal way to write it down. For the function x to y and the magnitude of x is greater than the magnitude of y, then there are elements for which x1 and x2 belong to x, such that x1 and x2 are the same and the function's value on those arguments are the same as well. So that's the formal way of writing the pigeonhole principle. Let's go to another question. So this is a question. If a department has 13 professors, can you say that at least 2 of them were born in the same month? Let's try to answer this question by identifying what the pigeons in this case are and the pigeonholes. The question is, the department has 13 professors. Can you say that at least 2 of them were born in the same month? What are the pigeonholes? So we are placing each professor into the pigeonholes of the months. So the months are the pigeonholes. So we have 12 pigeonholes where we place the professors who are the pigeons. So we have 13 pigeons and 12 pigeonholes. Does this suffice what we just read about the pigeonhole principle? If there are n pigeonholes, so there are 12 pigeonholes which are occupied by 13 professors. So that's n plus 1 or more. Then there would be at least one pigeonhole which will be occupied by more than one pigeon. That is, the department will have at least 2 of them born in the same month. So this is an example of the pigeonhole principle in practice. Let's look at something else. We were just talking about at least 2. Now, find the minimum number of balls required to be sure that at least one box has 3 balls in it. The question is, the minimum number of balls required to be sure that at least one box has 3 balls in it. So I don't know the number of pigeons. I know the number of pigeonholes, that is 2 boxes. What are the number of balls that I should have so that I can be sure that whichever way I place them, at least one box has 3 balls in them? 3 balls all would have to go in just the same box, and what would have happened if even a single ball goes into another box? So we would never have a surety that at least one box has 3 balls in it. So let's just say we had one more ball. So we now have 4 balls. The problem with 4 balls is I could have just put 3 of them in one and one in the other. But what happens if both of the boxes have 2 balls equally in them? So I would still not be sure that at least one box has 3 balls in it. Let's get another ball. Right? So now, if we have a 5th ball, wherever it goes, at least one box will have 3 balls in it. So when I required that at least one box has 3 balls in it, I required 5 balls to be sure of that. So let's try to generalize that. If n pigeonholes are occupied by kn plus 1 or more pigeons, where k is a positive integer, then at least one pigeonhole is occupied by k plus 1 or more pigeons. So in the question I needed at least one pigeonhole should be occupied by 3 or more pigeons, and there were 2 pigeonholes. So the minimum number of pigeons that I required were 2 times 2 plus 1, that is 5. This is the formal version of the extended pigeonhole principle, where the only change is that we had the magnitude of set x is greater than k times the cardinality of set y. And yep, that's similar to the pigeonhole principle that we formally wrote. Let's look at a question now. I'll give you a couple of minutes to think over this. Find the minimum number of students in a class to be sure that 3 of them are born in the same month. So try to identify the pigeons and the pigeonholes. The question is, find the minimum number of students in a class to be sure that 3 of them are born in the same month. So you have to place the students into the months. So what are pigeons? What are pigeonholes? Look at the extended version of the pigeonhole principle and find the minimum number of students required. As you can see on the screen, the number of we have to find the minimum number of pigeons required. Pigeonholes is 12. So just looking at the formal definition, you have n pigeonholes, so that is 12, n is 12, and you require that at least one pigeonhole is occupied by k plus 1 or more pigeons. So k plus 1 is 3 and k becomes 2. So now the minimum number of pigeons required, the number of students required is kn plus 1, and hence kn plus 1 is, you just place the values here. You have 12 times 3 plus 1, that is 37. So you require 37 students to be sure that 3 of them are born in the same month. It's a direct approach of the extended pigeonhole principle. So next we'll move on to the fundamental theorem of arithmetic. So this theorem just states that there is only one way to express an integer greater than 1 as a product of distinct prime numbers in increasing order and with positive integer exponents. This means that if there is a number n, it could be any integer number, and you want to write it as a multiplication of different prime numbers. What are prime numbers? So prime numbers are basically numbers which have which are multiples of 1 and the number itself, and they do not have any other multiples. For example, if I take the number 3, 3 can be, we can obtain 3 by just multiplying 1 and 3. There is no other way we can get 3. What about the number 4? Now 4 can be written as 4 into 1 and 2 times 2. So it has other factors than 1 in itself, and hence it's not a prime number. So there is only one way to write a number as a product of its prime number, of its prime factors. Let's look at the question. Write the following numbers as a product of their primes. You have three numbers: 180, 196, and 7344. Let's take a minute to try to find the answer. So you write it in terms of 2, 3, 5, 7, 11, 13, 17, 19. Try to write 180 as a product of these. And let's take a couple of minutes now. So the question, I'll just repeat the question again. You have three numbers: 180, 196, and 7344, and you need to write it as a product of the primes. So you write it as 2 times 3 times 5 times 7 times in their powers respectively. Try to identify the answer for this. We'll take 20 more seconds. Okay, let's look at the answers. So 180 can be written as 2 times 2 times 3 times 2, 2 times 3 times 5. So it's essentially 4, so it's 2 times 90, then 4 times 45, and so on. 196 can be written as 4 times, so it's 196 is 14 squared, so that is 2 times 2 and 2 times 7. And the difficult one was 7344 because it has a higher prime number as a multiple, and you would have to find, like, check for 11, 13 before you go to 17. So that's 2 raised to 4 times 3 raised to 3 raised to into 17. So that is your fundamental theorem of how many even divisors does 196 have? So try to answer this question, finding the prime factorization and finding the number of even divisors that 196 should have. Make sure you answer the number of even divisors and not just the number of even prime factors that it has. Take 30 seconds to answer this question. So 196 can be written down as 2 square into 7 square. We have three ways to choose the number 2. That is, we choose no 2's, 1 2 and 2 2's. And same thing for 7's, 0 1 2. So we have three choices for 7 and three choices for 2. Now if we want the even divisors, then we need to take at least 1 2. So we have two choices. We can have 1 2 or 2 2's in it. So we have 2 times 3 choices. So that's 6 even divisors that are there with 196. Prove that having 100 whole numbers, one can choose any 15 of them so that the difference of any two is divisible by 7. So you choose 15 of them, and any pair that you make out of the 15, they'll be divisible by 7, the difference of them. So try to identify the number of pigeons and the pigeonholes. A hint is the number of pigeons is the number of numbers you have. Let's take a minute so that you can try to understand the number of pigeonholes that are there. The question is to prove that if you have 100 whole numbers, so prove that having 100 whole numbers, so the minimum number of numbers required is less than 100. That's what you should be focusing on. Okay, let's look at the solution. The number of pigeonholes is, so every number, the 100 whole numbers, can be written down as 7k, 7k plus 1, 7k plus 2, 7k plus 3 plus 4 plus 5 and plus 6. It could be for any number of k's. So all numbers, let's say the number 8 can be written as 7 times 1 plus 1. The number 16, 6, can be written as 7 times 2 plus 2. Number 60, 60, can be written as 7 times 8 plus 4, right? So all the numbers from all the 100 numbers can be written in either of the 7 ways of writing 7k. Now, so you have 7 different forms of writing the numbers. Can they be your pigeonholes? So you just have to place every number from the 100 whole numbers that you have into those pigeonholes that are 7k till 7k plus 6. Right? So you have 7 pigeonholes and 100 pigeons. Let's check for the pigeonhole now. Try to understand what's going on here. Try to identify what variable n associates to, what variable k associates to, and try to find the minimum number of pigeons required, that is kn plus 1 here. Pigeonholes as 7. The number of pigeons that we already have are 100. The minimum number of pigeons that you want in at least one of them is 15, that is k plus 1. So now your k becomes 14, and the minimum number of pigeons that you need is kn plus 1, that is 14 times 7 plus 1, that is 99. So now we already have 100 numbers that is greater than 99, and hence if we choose 15 out of those 100 whole numbers that we already have, the difference of any two should be divisible by 7. And this is a really good example for the extended pigeonhole principle. Let's again go over what we undertook today. We started by defining what a set is, collection or of things or elements. We define what members of the set are and the two properties of the members, that they should be distinct, and the order does not matter. We define what integers, real numbers are, what negative numbers, what positive numbers, non-negative numbers, and non-positive numbers are. We defined finite and infinite sets, and the cardinality of a set that is defined as the number of elements in it and is denoted by these two symbols. We went over a question over the listing of the elements and finding the cardinality of the set. We try to write down sets from a given set. That these are subsets. Like there are A, B, C are the subsets of n given the certain conditions. We define what a function is, and then we try to draw an intuition of the pigeonhole principle. And we define an intuition that if n pigeonholes are occupied by n plus 1 or more pigeons, then at least one pigeonhole is occupied by more than one pigeon. That is exactly what we try to identify here, that you had 3 balls and 2 boxes, and you had to make sure that at least one box had 2 balls. So we identify the terms n plus 1 and n here. That's the formal definition of the pigeonhole principle. We did one more question on the pigeonhole principle where you had 13 professors and you had to make sure that at least 2 of them were born in the same month. Then we tried to draw the intuition of the extended pigeonhole principle where you wanted at least k objects occur in the same pigeonhole. Let's look at the intuition for that. That you have, if n pigeonholes are occupied by kn plus 1 or more pigeons, where k is a positive number, then at least one pigeonhole is occupied by k plus 1 or more pigeons. So you identify n, you identify k plus 1, you get k, and you find the minimum number of pigeons required in certain problems. That's the formal definition. We did a question on the extended pigeonhole principle where you wanted to make sure that at least 3 of them are born in the same month. We defined the fundamental theorem of arithmetic. That is, there is only one way to express an integer greater than 1 as a product of distinct prime numbers in an increasing fashion with positive integer exponents, where you wrote n as p1 raised to e1 times p2 raised to e2 times, like, till it goes on, the multiplication goes on till pk times e raised to k. You did a question on finding the prime factorization of the numbers. You wrote 180 as 2 square times 3 square times 5, 196 as 2 square times 7 square. These are prime factorizations where you just write it as the power, the product power of prime numbers. You cannot write it as 6 times 6 square because you have to break it down to the prime factors. You try to identify a question where you have to find the even divisors that a number has, and you found that it has 2 square, 7 square, and you found the number of ways 2 can be chosen and 7 can be chosen to answer this question. We did 2 more questions. The first one was another pigeonhole principle where you had to identify the pigeonholes, and this was the basic pigeonhole principle, where you just wanted to make a pair that is 2 pigeons in one pigeonhole. Then you did another question. There was the extended pigeonhole principle question where you had to choose any 2 numbers such that you had to choose 15 of the pigeons such that any 2, when you'd find the difference, is divisible by 7. You found the number of pigeonholes by writing it down, writing each number as 7 times k plus 1 plus 2 plus 3 till plus 6. You found out the number of pigeonholes as 7, and you found the number of minimum pigeons that you wanted was 15. So you had 14, so that's 14 times 7 plus 1, and that was 99. And we had the minimum number required. So we could say that if we had 100 whole numbers, one can choose 15 of them so that the difference of any 2 is divisible by 7. And yeah, I'm open to questions now.